So this video is looking at section 17.6, and this is kind of a key section because now we're going to start making the connection between entropy changes and enthalpy changes and spontaneity. Because so far what we've done is we've learned how to calculate both delta H for a reaction. We looked at that back in chapter 9 when we were doing thermochemistry. And now in this chapter we've learned how to calculate delta S for a reaction, but we still really haven't answered the question of whether or not that particular reaction is spontaneous. And so what we're going to do here is set up the reasoning behind this connection between entropy and spontaneity. And to do that, I think it's good to quickly review the three laws of thermodynamics. We've looked at these briefly before, but in a sort of shorthand define these, you can see longer definitions on Canvas or in your book. And so we have the zeroth law. And the zeroth law is that thermal equilibrium is transitive. And so what that means basically is that if A is at the same temperature as B and B is at the same temperature as C, then A is also at the same temperature as C. And so we can use temperature as a measure of thermal equilibrium. The first law is that the energy of the universe is constant. Or we could say the total energy of an isolated system is constant. Or another way we could say this is that the total energy of a system and a surroundings is constant. Because if you recall, the way we defined a system and a surroundings is the system is like the reaction, the specific thing that we're interested in, and the surroundings is the entire rest of the universe. The second law, and one that we're going to pay the most attention to here in this section, is that for any spontaneous process, the total entropy of the universe increases. There are a lot of different ways we can express this law as well. One way we could express it is that hot things cool down. In other words, heat always moves from hot objects to cold objects, not vice versa spontaneously. We have to add work. We have to do something to a system if we want to move heat in the opposite direction, like in refrigerators or air conditioning. And so this is what we're going to come back to in a moment. And then finally, the third law is that that only a perfectly ordered crystalline substance will have an entropy of 0, and that will be at 0 Kelvin, but we can't reach 0 Kelvin. So 0 Kelvin is sort of our absolute minimum temperature. We can't reach that. And so any substance that exists will have some non-zero entropy. But here we really want to focus on the second law because there's a connection here between entropy and spontaneity, because again, one of the ways we can define this is that for any spontaneous process, the total entropy of the universe will increase. And so we can actually express this mathematically. We could say that delta S total, or delta S of the universe, is equal to delta S of the system plus delta S of the surroundings. And so the surroundings is absolutely everything else in the universe. The system is the reaction typically that we're interested in. And we can tell whether or not a reaction, whether some process is spontaneous by the result here for delta S total. And we find that if delta S total is less than 0, then this process is not spontaneous. If delta S total is equal to 0, that means we have a system that is at equilibrium. Or we could say both the forward or reverse process is equally acceptable. And then if we would have delta S total greater than 0, in other words, if the total entropy of the universe actually increases, that is going to be a spontaneous process. And so this is our condition for spontaneity. If delta S of the universe increases during this chemical reaction that we might be interested in, that means that that will be a spontaneous process. So what does this actually look like if we start thinking about different chemical reactions and the relationship between the system and the surroundings? Well, I want to point out that you'll recall that a system can exchange heat with its surroundings. We can release heat to the surroundings if we have a chemical reaction that releases heat if it's exothermic. And likewise, we can have the system absorb heat from the surroundings. And so what we want to look at is what will happen in the surroundings if the surroundings absorbs or releases heat to the system. And so the way we're going to set this up is, suppose we have some reaction occurring in a flask or a beaker. And so this is our system. And we have the surroundings, which includes like the air around the beaker. This is the rest of the universe. And we know that delta S total is equal to whatever delta S is in the system plus delta S for the surroundings. Now, suppose we have some reaction inside the system that releases heat. So here we're looking at a reaction where delta H for this reaction is less than 0. This is exothermic. And so that means we have a reaction that is releasing heat to the surroundings. And likewise, we could look at the opposite, of course. If delta H were positive, if this was endothermic, we would be absorbing heat from the surroundings, and that heat would be going into the system. So now we want to think about what this will do to the surroundings. If I put heat into the surroundings, if I add energy to the surroundings, what will happen to these different gas molecules floating around in the surroundings surrounding the system? Well, if I add heat to the surroundings, I will increase the thermal energy of the surroundings. I'll have more motion. I'll have more molecular disorder and randomness. And so if I'm releasing heat to the surroundings, this will increase the entropy of the surroundings. So an exothermic reaction, if it's giving off heat to the surroundings, that will increase the disorder, the randomness, the entropy of the surroundings. So another way that we could write delta S of the surroundings is by connecting that to the enthalpy of the particular reaction that's occurring inside the system. And this will give us the appropriate units, because the units of enthalpy are in joules or kilojoules, and the units of temperature here are in Kelvin, so our units in entropy will be joules per Kelvin. And why is this negative? This is negative because if I have an exothermic reaction from the perspective of the system, it's the equal and opposite amount that it's experienced by the surroundings. So if I'm releasing heat from the system, I'm absorbing heat in the surroundings. So the change in the entropy of the surroundings will be equal to negative enthalpy over T. And this is very useful, because now what we can do is we can combine this with this expression, and we can calculate the delta S inside the system by just equating that to the delta S of the reaction, which we know how to calculate. So we can rewrite our third law expression to say delta S total is equal to delta S of the reaction minus delta H of the reaction over T. And what this will do then is give us a way to evaluate delta S total for any given chemical reaction. So if we calculate delta H and delta S for that reaction, we can calculate delta S total for the entire universe, system plus surroundings, and determine whether or not this reaction is spontaneous. Because again, if delta S is negative, it's not spontaneous. If delta S is positive, it is spontaneous. And we can now determine spontaneity using these values obtained from entropy and enthalpy changes for the chemical reaction itself.